Okay, today we're going to have a look at the Argand diagram. Now, the Argand diagram is very much, if not exactly the same as the Cartesian plane, but it allows us, and it's a special definition of a Cartesian plane that allows us to plot complex numbers. So on our Argand diagram, we know normally on a Cartesian plane we have the x-axis and the y-axis. On our Argand diagram we have a real axis, and now the y-axis becomes an imaginary axis. Now, something to keep in mind is that these, remember, are not numbers, but rather vectors. So, with our vectors, we can determine two things. Number one is the modulus, which is the distance from the origin to the point P, or the vector. And number two is the argument, which is the angle that the complex number makes with the x-axis. Now, we can use the following formulas to figure out the modulus and the argument of a complex number. The modulus is simply the magnitude of the vector, which is found by the square root of x squared plus y squared, and the argument is always found by going tan inverse of y on x, and of course we have to then consider what quadrant it's in, but we'll get to that later. Now, the argument is often given as between negative pi and pi, and we call that the principal argument. But often you can have an argument between 0 and 2 pi, and it is also correct. And it's important that you know how to convert between an argument between 0 and 2 pi and the principal argument, which is negative pi to pi. So example number 1 asks us to plot the complex number 1 on root 2 plus 1 on root 2i on the Argand diagram, noting its modulus and argument. The modulus, if we call this complex number z, the modulus of this complex number, mod z, is the square root of 1 on root 2 squared plus 1 on root 2 squared, which is equal to 1 if you type it into your calculator. The argument of z is tan inverse of 1 on root 2 over 1 on root 2, which is just 1, and tan inverse of 1 is pi on 4. So if we were to plot this complex number on the Argand diagram, we would draw a line. This is our vector, and this is the complex number 1 on root 2 plus 1 on root 2i, where this is the real axis, and this is the imaginary axis. Now, this complex number has a modulus of 1 and an argument of pi on 4. Now, this idea of modulus and argument gives us another way of representing complex numbers, which is the mod arg form. So we say that z, which is equal to x plus iy, can be expressed as r outside of cos theta plus I sine theta. And it's obvious to see why we call this mod arg form. So let's have a go at expressing 2 minus 2i in mod arg form. The first thing I do when I am doing questions like this is write or draw a little picture of where 2 minus 2i would lie. 2 is the direction of the real axis and it's positive, whereas negative 2 is in the imaginary axis. So it's going to be here with that 2 there and that 2 there. And if we add in our argument, we've got our theta. And theta, of course, is going to be tan inverse of 2 on 2, which is the same as tan inverse of 1, which is pi on 4. But since it's in the fourth quadrant, we could say that this is tan inverse of negative pi on 4, or 7 pi on 4, if you would like. Now, the argument of this complex number, the modulus, mod z, is going to be the square root of 2 squared plus 2 squared, which is the square root of 8, or 2 root 2. So in mod arg form, this complex number is 2 root 2 cos of negative pi on 4 plus I sine of negative pi on 4. And you're going to learn in the future all different ways that we can manipulate and change that. Often we write this as 2 root 2 cis. The cis stands for cos I sine negative pi on 4. However, they don't like you to use that notation as your final answer in the HSC. They're fine with you using it throughout your working, but not as your final answer. Now, we can use this idea of mod arg form to go back the other way. So to convert this into Cartesian form, we just have to ask ourselves, what is cos of pi on 3? And the answer is a half, plus sine of pi on 3 is root 3 on 2. If we expand that, we get 2 plus 2 root 3 I. But why do we care about this form? Well, it makes multiplication and division of complex numbers so much easier than what it did in the past two videos when we use those. So the multiplication of complex numbers in mod arg form, we just simply multiply the moduli and add the arguments. And for the division, we just divide the moduli and subtract the arguments. Now, sometimes it's easier to first convert complex numbers into mod arg form, then multiply or divide them, and then convert them back. So if Z1 is 2 cis 2 pi on 3, and Z2 is root 2 cis 3 pi on 4, find Z1 times Z2, and hence find the exact value of cos of 5 pi on 12. So Z1 times Z2, well, the multiplication of complex numbers tells us that we just multiply the moduli, which in this case is 2 and root 2 respectively. So 2 root 2 cis cosine sine. We add the arguments 2 pi on 3 plus 3 pi on 4. And that gets us 17 pi on 12. So 2 root 2 17 pi on 12. Okay. Now we need to ask ourselves, because often we don't like having our angle or our argument outside of what we call, and I've just realized I've missed the cis there, outside what we call the principal argument. And the principal argument is between minus pi on pi, and it's obvious that 17 pi on 12 is outside of this argument. Now 17 on 12 without the pi is a fraction. It's an improper fraction that is greater than 1. What I like to do is I type 17 on 12 in my calculator and I get 1.4. Now 1.5 if you typed it in would be 3 pi on 2, which means it would be your 270 degrees. So an improper fraction of 1.4 means we lie in the second quadrant. So that's 17 pi on 12 there. But those first two quadrants are pi. So if we subtract pi from 17 pi on 12, we get just this angle here is 5 pi on 12. So we've just realized, right, that that angle in there is 17 pi on 12. And what we can do now is construct a triangle. So we know that if we construct a triangle here, we're going to get the x value and the y value, right? And this is z1 times z2 here, the modulus of z1 times z2. So cos of 5 pi on 12 is going to be whatever the modulus of z1 times z2 is, but then we've got to use our knowledge of right-angled trig. So cos of 5 pi on 12, we notice that our 5 pi on 12 is there. Cos of 5 pi on 12 is going to equal x over the modulus of z1 times z2, which we know from up here is 2 root 2. So over 2 root 2. And we just need to figure out what that x is. And x is actually the real component of this multiplication here. So what we can actually do is figure out what that multiplication is by hand and then compare it to our answer and sub it in for x. So if we convert this to Cartesian form, well, 2 pi on 3 is negative 1, or negative a half, I'm sorry, so 2 outside of negative a half. And sine of 2 pi on 3 is root 3 on 2, so plus root 3 on 2i. If we pull that through, we get minus 1 plus root 3i. And if we do that in a similar way, z2 is going to be minus 1 plus I. So, minus 1 on root 2 and then I on root 2 outside of root 2, because cos of pi on 4, or 3 pi on 4, is 1 on root 2. And if we then expanded that, we get z2 is minus 1 plus I. Now if we figure out by hand what z1 times z2 is, just by hand, we go minus 1 plus root 3 times minus 1 plus I. If we expand that, we get 1 minus I minus root 3I minus root 3. And if we write that with the real components next to each other, and then the imaginary components here, we get that z1 times z2 is 1 minus root 3 plus I minus root 3 minus I. But we've agreed earlier that this x we were after was actually the real component of z1 times z2, which we've now figured out is 1 minus root 3. So the exact value of cos of 5 pi and 12 is 1 minus root 3 over 2 root 2, and that's done. Okay, thanks for watching.